Okay, today we're going to be talking about range query data structures, and essentially what that is just a bunch of data structures that can solve a specific type of query. And this specific type of query is one of the most important types of queries in like data structures in general. And it's a type of query that can be extended to paths on a tree. Like for example, in heavy light decomposition, which we talked about a few weeks ago, and it can also be uh it can be used in a variety of ways. So let's just get into how we're actually going to do range query. Range query. Okay. So range query is essentially a type of problem in which you have queries of the form update something and query the answer over the range L to R. So let's say you have, how do I annotate? Oh, oh my God. Okay, I guess I can't annotate. But essentially, if you have an array, let's say, for example, you want to update the value at I and query um the sum of all the elements from L to R, right? And so they're like this is like a very generic one, but it can get more complicated. Like for example, your update could be add phi or add x to the range from L to R, and query is perhaps the GCD over all elements in the range L to R, for example. And then you would need a more complicated data structure to solve it. And then it can go on and on and on. Oh no. Screen says loading. What? Let's see. Okay. Does this work now? Okay. Um, Okay. Well, range query is essentially like a type of problem where you have updates and queries, and for every update, it's like you update the at index I, you add X or change it to X, and then query the sum over the range from L to R, or the XOR or the GCD or whatever. And the more complicated the setup, generally you're also going to need a more complicated solution. And so knowing the basic setups and basic solutions is going to help build towards this more and more complicated problems and solutions that come with them. So the first data structure that I'm really going to focus on is a sparse table. And while a sparse table isn't necessarily the most used out of all range query problems, it is still a very useful data structure that is worth knowing, especially in particular instances where you might want to use a sparse table over, for example, another data structure that we're going to learn today, binary index tree. Sometimes you might actually want to use a sparse table over a binary index tree for very, very specific applications that are actually very common. So what are sparse tables? Well, sparse tables are a way to solve range query problems without updates. So it's not actually a true range query, but it's essentially without any updates. Um, the idea is to store for every index I and for every k, we want to store what basically what the answer is from I up to 2 to the I. So let's say we have a sparse table that stores the sum, right? So what would happen is for every I, for every index I, like you want to store the answer within the range from I to I plus 2 to the k. And for example, let's say your array is 1, 2, 3, 4, 5. Then and then like let's say k is 2, right? So then from index 1, you go to index 1 plus 2 to the 2, which is 4. So the answer, or at least st of ik or st of 1, 2 would be the answer from 1 to 5, which is the sum from 1 to 5, which would be 15 in that case. So let's say we want to calculate this quantity. How do we do that? Well, actually, we can use binary lifting to do this. So the idea is basically, it's actually very similar to the way we calculate LCA, but essentially the idea is once we've calculated one layer, or basically for every K or for every I at a particular K is like one layer. Once we've calculated one layer, we can build another layer on top of it. So we would have ST of I K plus one would just be adding the two children together, and the two children are um I K, so the first half essentially, and then you have to go to the next half, which is I plus 2 to the K, which is the next half, all the way to the end, which is pretty nice. So now that we have all of this calculated, we want to combine all of this efficiently to query it. And while like it might be very complicated to do an operation like sum or XOR or something that like adding overlaps would change the answer, we can actually do this really easily when whenever adding overlaps will not affect the answer. And when adding overlaps does not affect the answer, are three really common queries or types of operations with min, max, or GCD. Because what I mean when overlapping doesn't affect the answer, it's kind of like if you've already included a, like if somewhere you've already had a within your min or max, then minning that with a again won't do anything. Similar for max. If we've already taken the max of everything, including a, putting a again, like maxing that with a, won't change the answer at all because you've already maxed a. So this allows us to like essentially overlap the ranges, and we don't have to care about like exactly where we start or end. All we need to care about is that both ranges cover the entire length of the interval. So in order to make it so that both cover the entire length of the interval, then we basically want to essentially have one cover the first half and or not or even more than half, and another cover the last half. And the way we can do that is we can basically calculate the log of the range. And once we calculate the log of the range, that one st, like the value we have in our sparse table, is going to cover the first half of the range and the last half of the range, which is actually very nice. So the answer would just be this expression over here, st of L log, and this basically covers the first half, or actually a lot more than the first half, and then st of R minus 2 to the log times and then log, and this covers this next half because you're starting at R minus 2 to the log and you're working all the way up to R. So this covers the entire length of the interval, and because overlaps do not affect the answer, this works for min, max, and GCD. However, in order to do something like sum or like XOR or something where it's like cumulative, this idea won't work because this will actually overlap in a lot of places. And when it overlaps in a lot of places, it'll change the answer and you won't be able to do this. So in order to account for overlaps, if you wanted to do sums with sparse tables, you would essentially do the same thing, except here when you do st of L log, you're covering the first like bit of the range. So you just calculate, okay, when does this thing end? It ends at L plus 2 to the log, right? So your next one is going to be L plus 2 to the log plus 1 to and then that range to R, we can just recursively do it. And every time the remaining range decreases by at least a factor of 2, so it'll still take log n time, but it's still better than a naive solution. So if your operation is like addition or multiplication maybe, or XOR, or um something like that, right? You would have to use O of log n to do this. But if your thing is min or if it's max, or if it's or and or bitwise or bitwise and GCD, something like that, where overlapping does not affect the answer, then you can use the sparse table to actually do it in O of one time, which is very, very cool. And one application of this idea can actually be used to do LCA in actually O of one time. So I talked a little bit about how to do LCA in O of log n time per LCA query. Using sparse tables, you can actually turn it into O of one time. Um, and the idea behind that is you can take an Euler tour of the whole tree. And once you take an Euler tour of the whole tree, you can realize that the LCA between A and B is literally just the minimum of the indices um, between A and B if you do some like Euler tour and then assign new indices to every node. And then once you do that, you can use a sparse table to calculate what that min is and then convert it back. It is a little more complicated than the traditional binary lifting method, but it is nevertheless something that is extremely useful. And sometimes you do need O of one LCA. So you would need to know how to code a sparse table in order to do that. So yeah. Yeah, and I talked about this a little bit, but pre-computation time, as you can see, is n log n. So is the memory. Memory is also n log n. But the query time is O of one if you're using one of the operations that are like very good for sparse tables, like min, max, GCD, bitwise and bitwise or are just a few examples. But if you're using bitwise XOR or like sum or multiplication or some sort of any sort of operation where it's cumulative, then you wouldn't be able to do it in O of one. You need to do it in O of log n. And yeah, I already talked about how to do O1 LCA briefly. So let's move on to the next problem. Or the next data structure. And the next data structure is binary index tree. And this is actually a relatively complicated tree, but it's very easy to understand that it works and understand what it does. And generally, you won't really need to use the intuition behind binary index trees. Binary index trees are actually very similar to segment trees, but the difference is like, at least in my opinion, segment trees are a lot easier to understand, a lot harder to code, but also you have to understand segment trees because you need to manipulate a segment tree to do exactly what you want. With binary index trees, there's not much to manipulate, and so binary index trees are typically a lot more basic than segment trees. So without further ado, let's get into exactly what a binary index tree is. So a binary index tree essentially solves this following problem. It is a range query problem. Essentially, it's you want to update point I, you want to update the value at point I, and you want to find the prefix sum of like, so your query is just querying for the prefix sum. So your updates are at a single point and your queries are for the prefix sum. And as you can see, this is actually very useful because um it's like kind of like updated prefix sums. Like if you use prefix sums, you wouldn't be able to update, but with a binary index tree, you can do a lot of really cool things by updating particular positions and then calculating prefix sums. And yeah. Well, how does a binary index tree work? It's very, very, very complicated, but here's a very simplified version of how it works. So first, what you want to do is you want to construct a binary tree on the array, and each node is essentially like, think of it as contains um like a particular range within the array, and its children are like, if you split it directly in half, then the left child is the first half, the right child is the second half. But with a binary index tree, you don't actually store the whole tree. You can actually implicitly only store the first half, the left child, because once you know the left child and what the parent is, you can implicitly figure out what the right child is. And so that allows us to save a lot of memory, but most importantly, it actually allows us to cleanly use bitwise operations to manipulate the answer. And the way we can do that is we essentially realize that if we're storing all of this, we can actually, instead of like just storing the tree structure and storing the children, whatever, when we implicitly only store one of the children, you can actually realize that there's only exactly n nodes. Like if your array is of size n, and you implicitly only store one child, then actually turns out they're exactly n nodes. And once they're exactly n nodes, you can basically put all of the nodes on a single array. And once you put all of the nodes on a single array, it turns out that with clever bitwise manipulation, you can actually update and query all of the nodes in the required prefix sums. So for example, when you're updating I, all you need to do is figure out all of the things that contain I and update those. And the way you would do that is you could really cleverly figure out, like, if it's a left child, then find the next parent that is also a left child. And if it's the right child, or essentially you want to basically figure out the next parent that is also a left child, and to figure out it, like, and to query, you would basically have to uh go from the beginning. It's kind of like binary search, where if it's to the left, you go down without adding it, and if it's to the right, you add the left child and then you go to the right. So yeah, this is one of the data structures you really do not really need to understand. So you can essentially just black box it, and you know what it does, you know how to use it, but you do not need to know how it works or why it works. You just need to know how to code it, and or perhaps memorize the code or whatever. And also you don't need to know why it works. So because you don't need to know how it works or why it works, I just thought it was a good idea to put some code here. So I can explain this code a little bit. So the update function finds, like, essentially it updates the value at position I, or in this case position pause. And here the X is you're adding X to position pause. Sum is just finding the prefix sum at R, and query is going from L to R. It's in a similar way to how we would query in a prefix sum. So for updates, what we see is, if we do the pause and minus pause, if we add pause and minus pause, it turns out that actually gives us the next left child that or the next the lowest parent that particular node that's also left child. It actually just gives us that. So it's a really nice way of just keep doing that until it's too big. And then once it's too big, you just stop updating it because you don't need to update it anymore. And it's actually a really, really cool way of using bitwise operations to update every node you can. And it's very similar with sum. If you do this exact bitwise operation, what you can do is you can actually start from R, and basically you take R and then you go to the next thing that ends at the one previous to R, basically. And then you keep doing that until you reach zero. And once you reach zero, you've finished finding the prefix sum of everything. So yeah, this is how this is basically how binary index tree works. So here's a sample problem counting inversions. So you're given an array A of size n, and an inversion is a pair of indices I and j such that I is less than j and AI is greater than AJ. Um, yeah, and I'll give a few minutes to think about and solve this problem. Okay, so now I will explain essentially how you would solve a problem like this. So the first thing you think of is let's try to directly count it, right? So let's say we want to figure out how many indices, like let's say we go from 1 to n, and we want to figure out, so once we're at index I, how many indices are less than I such that their value in the array is greater. And this is actually a relatively complicated problem to solve because um you would need to like you would essentially need to figure out, well, okay, so I have this array value, and well, okay, so if everything before it was like, or you'd have to figure out how many things before it were greater, and that's not the easiest thing to do. So the easiest way to think about this problem is actually to instead sort the array first. And what you want to basically process all of the values in the array from smallest to largest. And the reason why you would do this is because let's say you had let's say you had uh let's say you've already processed the first few elements, right? And now you're processing one element. The reason you would want to do this is because out of the first few elements, you know that every single one of them is less than your current element. And you also know that everything you haven't processed yet is bigger, right? So now all you need to do is query to the right of the position how many of the things to the right of the position are less, and basically how many of them are processed already, or how many to the right, or how many to the right are processed, and so on. So you would basically be able to count inversions in this way. So the idea is you process each element in sorted order. Once we sort the array, we can basically process the element. And what process the element means first you query for how many inversions does this element contribute to the answer. And the number of inversions that this element contributes to the answer is essentially the number of elements that are less than it to the right. And we can use the binary index tree to do that. After we do that, we update the element. So all in the binary index tree, everything starts at 0. So when we're processing it, we first query from I all the way to n how many are already processed, basically the prefix sum. And then after that, we update I to 1, and then we process the next element. And this is actually a really neat way to do this. And in fact, there are other ways to use binary index tree to actually solve this problem. You don't actually need to process each element in sorted order. As long as the elements are below a certain threshold, like you can store it within a binary index tree, you can actually also use a binary index tree directly. Because if you think about it this way, right? If you go from left to right and you're processing the ith element, that means that um all of you basically want to figure out how many elements to the left of it are greater than it, right? And the way you do that is when you're processing the element, you add one whenever you're you add one to the index, which is equal to the array value at the point you're at. And what that does is it essentially maps out how many ones there are before the index you're at, how many twos there are, how many threes, fours, etc., all the way to the maximum possible. And then you just need to query from this number all the way to the maximum number, how many elements already exist within that. And the answer to that is just um the is just how many inversions that this particular element contributes. So if you sum all of that up, that would also give you the number of inversions. um yeah, so this is a pretty nice way to use binary index tree to solve a relatively complicated problem. Um, yeah, and I believe that is it. So Yeah.